Hey guys, this is the right time to apply all knowledge and skills you've got during all the previous videos. So I just remind you that all previous videos were dedicated to inequalities, so how to solve inequalities by graphing or using graphs. And here is linear linear programming problems that actually represents the real life applications of those theoretical bases that we actually explored before. Okay, so the first type of problem that I want to consider today is a manufacturing problem. So in manufacturing problems, we need to determine probably the number of units of different products, of different mixture of products, which should be produced by the company or by the firm and sold on market, so that each product requires different consumptions, so material consumption, manpowers like labor force in terms of different labor hours, machine hours as well, probably other consumables and components in order to make profit maximum. So that's the main idea of any business, right? So key stakeholders, actually the owners of the business, they track the idea of maximizing profits. It's not like the primary goal, but this is definitely commercial goal of any business. All right, let's get to the problem and see what we can do here. So that's manufacturing problem, and the manufacturing company produced two types of tables, a 2-drawer table and 3-drawer table. So each with locks in it. So on stock, there are only 20 locks and 30 meters of wood sheets. Okay, so that's material. So drawers need to be purchased in bulk from a supplier who sells at least 18 drawers. It means one batch contains at minimum 18 drawers, or at least 18 drawers. Here is the table below showing the consumption of materials and of the components for each type of tables. So we're going to see that the two types and each require different locks and different wood consumption. Alright, so if a 2-drawer table earns $15 per unit sold and 3-drawer table earns $20, determine how many tables of each type should the company produce in order to maximize profit using materials and components that are available in stocks and only in drawers bought from that supplier. Okay, so try to pause the video, try to explore by your own, and here I'm going to start. So what I'm going to do, the first and logical step here is to set up constraints. But before setup, we need to have variables. In this case, I'm going to set up number of each type of the table. So 2-drawer is going to be X, and Y stays for 3-drawer table. So basically this is the quantity of each type of the table. So we have X for 2-drawer and Y for 3-drawer. Okay, so let's go to constraints, and right now I'm going to consider consumptions basically. So constraints in this case will represent consumption of different consumables, of different materials and components. In this case, what components we have? We have locks, and it's probably reasonably to start from there. So in stock there are only 20 locks. So we've got 20 locks, and that's why I'm going to set up the first inequality for those 20 locks available on stocks. So that's why if X consume 1 lock, so in total for X 2-drawer tables will have X locks, and 3-drawer table which is Y consumes 2 locks, so we add 2 Y's basically, and that's constraint is going to be as inequality. So we are going to set up less or equal than 20, because in maximum we have 20 logs on stocks. Okay, so that's the first one. So next one, 30 meters of wood sheets, and X will consume 3X, and 3-drawer table, which is Y, consume 2Y in total. So that's the total consumption of wood in meters squared. So, and the requirements should be less or equal than 30 meters squared. So that actually wood consumption. So wood consumption. So let's go next. That's the key idea about drawers. So drawers, there are no drawers at in the inventory, so at stocks. So that's why the company need to buy it from supplier. But supplier can sell only in batch minimum 18 drawers at least. So it means in one batch is going to be selling only 18. This is the minimum quantity that the supplier can sell. All right, so let's arrange inequality for drawers. So I put dr stays for drawers, and right now we're going to have the following. So what about drawers? 2-drawer table obviously will consume 2x drawers, and 3-drawer table will consume 3y. So that inequality is going to be more or equal than 18. So why more equal? Because it can, so the supplier can sell at least 18 drawers. So we cannot buy less than 18. So but actually we can buy any amount. So we are not limited on the top from the top. So there is no supreme, okay, supreme boundary, what is called. So actually we set up all the constraints right now, and this is the system of inequality. And right now what I'm going to do, I'm just going to set up our objective function. So let z is objective function, so the general way to represent in linear way is ax plus by. So a and b coefficients. So what stays for coefficients and what stays for objective function? This is the profit, so I'm going to write that this is the profit. So profit with ax plus by. So in our case, the target function or objective function is going to be $15 2-drawer table earns. So that means we're going to set up 15x. That's the total profit from x units sold. And on top of that, we're going to add 20y. All right, so we set up an objective function. So objective function. So we set it up. We set up all the constraints except for the last, because right now what we know that quantities x and y should be positive values, right? We can't sell negative values. So this is a real life problem. So on top of that, what I'm going to do, I'm just going to say that in this system we also need to include non-negative conditions. So that's why x more or equal than 0 and y more or equal than 0. So now we have complete constraints including non-zero inequalities set up for x and y quantities. All right, so everything ready, and we can go to actually drawing the region according to the first step in our methods, right? Just remember vertex points methods, so that we are going to first of all set up the region, draw it up, and then define value z at the vertex point, so at vertices. And then we also need to judge about what sort of region we have. Do we have bounded region? In this case, that's okay, it's convex polygon, so we just need to take care of value z and vertex points. So if it's unbounded, we need to make like first decisions about inequalities as I considered in the previous example when we had an unbounded range. So then we need to actually consider how to do, so does this half of the plane, if we consider inequality for z, does this half of the plane have common points with the region? If it doesn't have, okay, so we've got the minimum value or maximum value and the vertex. If it does have, so we need actually to explore further, and in most cases we actually come to the idea that this function z won't have any optimal value. All right, so that's words, but let's go to the practice. So I'm going to, highlight that. Okay, yeah, perfect. So I'm going to cut that and paste on the next slide, which is here. Oh, okay, yeah, I just remembered that I set up, and that's cool. So I'm going to set up that. Perfect. That's our constraints. And also what I'm going to do, I'm going to set up z function as an objective one. So we already set it up, but we need to also transfer. Now guys, I know how to do that. It's a bit tricky way to do, but anyway, don't have any other options. All right, so that's our objective function, that's constraints. Now we can work normally with that. All right, so right now what I'm gonna do, I'm going to say that, okay, I'm going to say that constraints over there, that's good, that's constraints. So in the bottom part, that's non-negative conditions. So one more time, constraints and non-negative conditions. All right, so let's try to build it up. So let's try to build our region. So the first, let's consider the first one. So probably this one is better to consider. So that's simply x and y axis. So we actually in positive quadrant where x and y both positives. That's okay. So I'm going to start with that one, because in this case we have y more or equal than our function. So I just want to reset up and say, okay, for drawers, so for drawers we have 3y more equal than negative 2x plus 18. So in here you actually can set up the points if you like. 6 is gonna be, it seems to me, yes, 6 is gonna be y-intercept and one more point. So when y is 0, x is 9. Okay, so yeah, you guys actually can do it by your own. We did it many times, so that's why my first line is going to be here. Okay, you know, even I can mark as the color, so I can choose any color, let's say red. So that's for that line. I'm going to use red color. So if you have this option, try to use the same. So now I'm going to set up that line that goes in this way. So more precisely. Okay. Yeah, perfect. That's the line for drawers. So I can actually put the word drawers here. That indicates we set up that. Okay, so next one, let's set up logs. They're here. So logs is going to be, oh, by the way, yeah. So 3y more, so where's our region? The region above the line, right? Okay, so about logs. 2y less or equal than negative x plus 20. Okay, so for that line, I'm going to choose, let's say, so 20, yeah. Yeah, it's 20. So I'm going to choose, let's say, blue one. All right, set that for logs. So 10 is going to be y-intercept, and when x equals 0, sorry, y equals 0, I'm going to say that x is going to be 20, yeah? So it goes through 20, and so where's 20? 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be 20, I guess. Okay, and now I'm going to set up that line that goes through 10 and 20. All right, so we got that. So next one, next, wood. Okay, so we set up wood, and here we're going to have 2y less or equal than negative 3x plus 30. Okay, so for that, I'm going to choose the green color. And so what about y? Y is going to be 15, I guess. Yeah, so 15 goes from there, from very top. So I don't have these options here, but anyway. So what about x-intercept? It's going to be, so what about x-intercept? It's 10, yeah, it's 10. So the line goes through 10 and through 15. So 15 is pretty far, but anyway, it looks like that, okay? That's 4, yeah. So 15 is going to be there. If I'm correct. Probably not. So it's better to find one more point, because you see that the green line will intersect with blue line, and we need to find this intersection point as the vertex. So anyway, we need to do that. So what I'm going to do, I can say that the wood compared with logs, right? That's intersection. So if I equate them as lines, I'll get negative x plus 20. That's how I can find the common point of intersection. So from where I see it's going to be 2x and 10, so x equals 5. So from there, I've got x equals 5. This is the point of intersection. So we set up that point. So, and we come back here. So it's going to be that point. That's going to be the vertex. So, and by the way, it's going to be an intersection point. So the value is going to be 7.5, I guess. So that's 7.5. So that's the point of intersection. We'll need this 7.5. That's the second coordinate. All right, so y is 7.5. You can check by your own, guys. So in here we are going to connect. So your green line for wood should go through one more time. So y is going to be 15. Oh no, sorry. X-intercept is going to be 10, and the second point is that one. All right, so that's how it goes. Okay, so we set up everything. We've got no negative conditions. So where's our region? I'm going to shade that right now. Let's shade with that one. So let's have a look at inequalities. So for logs, which is that one, we have 2y less or equal than. So it's a blue or indigo color line, so y is going to be lower. Okay. We also have non-negative conditions, right? So about the red lines drawers, remember, the company can buy it or order from a supplier in the quantity of at least 8 in drawers. So that's why we have 3y more equals, so that's correct. And about green line, wood is going to be used less than 30, so 2y is going to be less than the equation of the line. So we set up our region, and hopefully it's bounded. So our region is bounded, so we can highlight that. Right now, region is bounded, and that's cool. So R is bounded. so we won't have any problems with z-value. Now we're going to calculate z-value at the vertex point. So how many vertex point we have? So we have that one. So we've got the first one, the second one, third one, and here also too. So we've got actually pentagon in this case. All right, so let's calculate the values z in any given vertex point. So let's try to do it right now. So the first, this is one. So 0, 10. So 0, 10, we actually got z to be equal to 200, right? So z, oops, let's change the size. So z at that point is going to be 200 bucks, right? Dollars. So next one, so 0, 6, we've got 6, 120, yeah? I guess 120. That stays for z at that vertex point. Okay, so let's go next. 9, that vertex, which is 9 and 0. We've got 9 times 15. And in this case, we're gonna have 135. So z here is going to be 135. And here, 10 is simply 115. Our objective function dollars. Can use dollars everywhere. And the last point. So actually have a look. We've got not an integer value. So what it means? It means that for wood, actually we can use, but for logs, it's impossible. Actually, for wood, we can use decimals. So for any quantities that measured like length, like area, like volume, we can use decimal, so fractional parts. What about logs? We cannot set up half a log, right? It won't work properly then. All right, so that means actually we come back to the integer points within the region, and we need to actually find all integers in this case. But anyway, let's try to calculate and try to have the real maximum value, real possible value that we might have. So, and if we plug 5 and 7.5, we can get that z is going to be 225. This value is impossible due to 7.5 of logs, right? 7.5 logs, yeah, 7.5, yeah, it's impossible to have fraction quantity for logs. So that's why this is not like this value, it's non-achievable value for the profit. So what are we gonna do? We can actually try to find the nearest whole values for our region. So right now I'm going to set up all the values within the region using, let's say, which color to use. Okay, let's take green one. So that's going to be our possible whole values for logs. Actually, for wood we can use actually fractional one, right? Can we? Yes, we can. So let's go there. So we just move at the boundary and within the region. So actually we're going to set up all values that are non-fractional. So here as well, and here. It seems to me that that's pretty enough, because right now we are going to calculate the values in integers, so in integer points. So what do you think, guys? What's the best value that actually it seems to me that the profit can be achieved. So you know the good actually shortcut for you, if you set up the equation and write 15x plus 20y equals to $225, you have at least a benchmark line which allows you to figure out the slope of your line. So you can set up and see the gradient. So actually your line might have, let's say, if I do it in the software, so for example, if I set up that line, I'll get the line that will go something like, let's say, our target line. Use the black one. So our target line will go through 9 something, a little bit something, in your point, your vertex points. So that's definitely the maximum, right? 225. But it's not achievable, so it's nearby, like it's probably 11. Yeah. So that's how our function will go. And you understand that if you take care of this slope, right, you can use the parallel shift so that now it will go through that point and with the same slope, right? And as you can see here, there is one more point that actually can be candidate for our maximum profit. But let's see. So if we get 6, we have also 7. Yeah, I guess. Okay, so we need to test this value as well. So right now we are concentrate on those points that are actually candidates. So that point, and that point, they're candidates for maximum profit and using integer points. Okay, so let's try to calculate right now. So if we take coordinates for that and calculate the value, we've got 4 here and we've got 7 here. And what if we plug that? So simply we can plug x equals 4, and in this case we've got 7 only. And we'll get z equals to 200. So it's definitely less. So let's calculate that point, in that point z. So here is $200. If we calculate taking 4 and obviously more in this case logs, right, and more drawers, why 3 drawer tables. So actually we can figure out that 4 and 7, or even 8, I guess, yeah, 8, we've got $220. That's very close to our ideal value if we used fractional. So right now it's sort of a target value, and I just simply highlight that for a moment because that point is actually we interested in. But we also need to check another point, which is here. So let's try to do that. So 5 and 7. So if we calculate in 5 and 7, and 7, we'll get 215. So very close but lower. And we just go down, you understand that you basically diminish the value of y's while the number of, let's say, of 2 drawer, that stays for x. So that's 2 drawer tables. You actually will increase that type of the tables, but it seems to me that it's going to be lower, maybe around, I don't know, but let's calculate. So 5 and 6 right now. So we've got 5 and 6. Yes, if we calculate 5 and 6, we'll get 195. So as you can see, the lower we go, the less value we have. However, what if we take, let's say, 6 and 6? That point also might occur. Let's calculate the last point. So we've got 6 here, the coordinates, and 6 here. Let's calculate z. In this case, it seems to me 6 and 6. Yeah, right. We've got $210. So that's not enough, right? So definitely the maximum profit will be here. But can we like check that point as well? So probably it might deliver more profit. Let's do it. So I just try to, I don't have really a lot of space, but let's try to do it here. So let's try to calculate z. So it's going to be definitely 2 and 9, right? 2, 9. Okay, so let's plug 2, 9. And we'll get 210. That's definitely lower. Okay, so looks like that is going to be a maximum value. So if you're be able to check all the whole regions, but it's pretty a lot, I'm not going to do that. So you can just figure out that values within the region is going to be probably, definitely should be lower than we calculate than our absolute maximum for now, which is 220, and that's the solution. All right, so having that, what we actually need to do right now, because the question was how many actually drawers, tables of each type of drawers, like 2 drawers. So basically how many drawers we need to have in this case. All right, so we actually did it. If we set up, let's say, we've got right now what we've got that maximum value is achieved when z is 220 and we have also the coordinates. So for x, which is actually 2 drawer tables, and y equals to 8. So that's going to be the maximum value. 3 drawers. It's going to be the maximum value for our profit, which is $220. Okay, guys, hope you understand. Yeah, it was a little just long way because actually due to capabilities of the software, I cannot like zoom in, I cannot like shift to the place whenever I want it. So due to those constraints of the software, I had a little longer to go through. But anyway, we've got the idea. You can do by round. So if you do it quick on grid lines, definitely you will do it faster. Here is my explanation. So some comments on exams, you definitely waste less time. Hope you like that. That was manufacturing problem. And at this point, it seems to me it's reasonable to switch to trigonometry and vectors to finalize those topics for GCSE. So don't forget to subscribe if you're new here to my channel. So actually you can explore a pretty lot. There are lots of topics, more than 100 videos. So dedicated to GCSE. Have a deep dive, try to explore, share the comments. What do you want to, or what do you expect to see in nearest future, and I'll give you feedback, guys. That was Daniel Dallas. Peace out.